Okay, good morning. This is Physics 1151 here on Thursday. Today we're going to start Chapter 25, which deals with electric potential energy. Um, so we're going to go over a little bit about the analogy between gravitational and electrical forces and fields. Then we're going to get into work and potential energy, and then conservation of mechanical energy for a charged particle in an electric field. And you have a homework coming up on chapter 23, and we're actually a little bit ahead in lecture, so this lecture will be a little bit shorter. So let's quickly review gravitational force. So if you recall physics 1150, one of the primary forces that you discussed was the gravitational force, primarily between the Earth and some mass m that's located on or near the Earth, right? And you can describe that force in terms of Newton's universal law of gravitation, right, which relates the force exerted equal and opposite between two bodies, mass 1 and mass 2, to the distances between them and along a radial line between the two bodies. In other words, the force is always attractive, okay? And then near the Earth, if the first mass is the mass of the Earth and the second mass is the mass of some body interacting with the Earth, we can put in r as our Earth, right? Since the distance between you and the center of the Earth is roughly the radius of the Earth. And when you lump all of these constants together, that gives 9.8 newtons per kilogram, or 9.8 meters per second. And they're the same units. And this you call G, right? And G is what is called the gravitational field strength near the surface of the Earth. And near the surface of the Earth, since we can use the flat Earth approximation near the surface of the Earth, hopefully none of you believe that the Earth is flat, but we can approximate it as flat near the surface. And if we call y the vertical direction, we just describe the gravitational force as mg in the negative y direction, where g is all of this other stuff but the mass lumped into a constant. Okay, now if you get much above the surface of the Earth, then r is no longer exactly equal to r Earth, and then this value of g decreases by a little bit. But as long as we're not too far away from Earth's surface, and even up to higher values if you adjust g, we can describe the force in terms of mg, where g is the gravitational field strength. Okay, now you also recall, hopefully, from Physics 1150 that forces are vectors, and it's often easier to describe the interaction between the Earth and some mass m in terms of energy, right? In terms of potential energy of the interaction between the mass and the Earth. And you derive that this quantity called the potential energy, gravitational potential energy, which was mgh, right, where h was the height above the Earth, and you defined the 0 point of the energy at zero, at the surface. Okay, now if you look at the equation here between the gravitational force and the Coulomb force, the electrostatic force, the equations are nearly identical, right? Instead of mass, we have charge. We have a different constant. It goes as 1 over r squared, and it's along the radial direction. Okay, now one difference is that the electrostatic force can be attractive or repulsive depending on the signs of the charges, whereas gravitational is always attractive. But these equations, this 1 over r squared dependence gives rise to the fact that both of these forces behave very similarly, okay? And they're what are called conservative forces. In other words, if you calculate the work done by each of these forces in moving a body or a charge between 2 points, the work doesn't depend on the path taken, okay? And that allows us to define, similarly to gravitational potential energy, this quantity called the electric potential energy, electrical potential energy. And we'll find that this is also a much easier way to describe the interaction between charges than having to deal with this force all the time. Primarily because with energy you're dealing with scalars instead of vectors. And there are some quantities there's a quantity related to the electric potential energy called the electric potential, which has a symbol V. We often call it the voltage, which is very easy to measure. Okay, so it's usually much easier to deal with energy than it is to deal with forces. So we're going to borrow some of the tricks that we learned in Physics 1150 and dealing with gravitational potential energy, and we're going to apply them to this quantity called the electrical potential energy. So let's go back and briefly start with a quick review of work, because work is related to potential energy for both of these forces. So you recall from earlier in this course and in Physics 1150 that if a force F displaces some body by a distance delta r, that the work is obtained by integrating this dot product or scalar product of F dot dr. Okay, and what that evaluated numerically is the magnitude of F times the magnitude dr times the cosine of the angle between the force and the displacement. Okay, and if the force varies along the path, we have to do an integral. But if the force is constant along the path, in other words, if this is a uniform force field, in other words, the force doesn't vary along the path, it's constant, kind of like gravity near the surface of the Earth, then we can pull this out of the integral and the work just becomes F times delta r, where delta r is the displacement and the cosine between them. Okay, this is the magnitude of the work. And work is a scalar. It's a dot product, okay, where F is the magnitude of the force, delta r is the magnitude of the displacement. Okay, important point here, this is always positive. It's the magnitude of this vector delta r, and theta is the angle between the force and the displacement. Okay, so that's work. And here's an example. If the force and the displacement delta r are in the same direction, then theta is 0, cosine of 0 is 1, and the work is just F times delta r. It's positive. If the force is applied perpendicular to the displacement, then the angle between the two is 90 degrees, cosine of 90 degrees is 0, and so the force does no work. Okay, and then finally, if the force and the displacement are in opposite directions, for example, air resistance or friction, then the angle between the force and the displacement is 180 degrees, cosine of 180 degrees is -1, and the work is negative F times delta r. Now it can be any other cosine can be any other angle, but these are the three different limiting angles. So if the force is conservative, as gravitational force is, and the work is independent of path, then in Physics 1150 you defined this gravitational potential, UG, such that the work done by gravity is the negative of the change in the gravitational potential energy. This should be negative of UG minus F at RF minus UG at RI. So these RF and RI have got to flip. But the work done by gravity leads to a negative change in potential energy. So in other words, if gravity does positive work, meaning it pulls a ball down toward the surface of the Earth, work is positive, the potential energy of the ball decreases. Okay? If negative work is done by gravity, such as when you throw the ball up in the air, then the displacement and the force of gravity are in the opposite directions, work done by gravity is negative, and there's an increase in the gravitational potential energy. And so we're going to define a electrical potential energy using this same equation. We're just going to have a different equation for work because the force is slightly different. So here's an example of gravity again. Just going back because there's if you can understand gravity, it's a simple step in understanding electrical. So here's a uniform gravitational field, okay? And that, in other words, you're close to the Earth's surface. The gravitational field strength, G, is constant. It's 9.8 newtons per kilogram, pointing downward. And so if, for example, you have a ball, and you throw the ball up and the ball is falling down, the force of gravity and the displacement delta R in this case, gravity is negative y direction, and you can take the dot product, which is force dotted with delta R, and the force is in the negative y direction. And in general, if you have three-dimensional motion, delta R would be delta x along the x direction, plus delta y along the y direction, plus delta z along the z direction. And when you take this dot product, the y and x vectors are perpendicular, the y are perpendicular, and the dot product reduces to negative mg times delta y. Okay? And so then the change in the gravitational potential energy is the negative, is mg delta y, and it's mg y final minus mg y initial. And you've covered this in Physics 1150. And so in this case, y final is less than y initial. They're both positive. And so the change in the work done by gravity is positive, and it leads to a decrease in the gravitational potential energy. Okay. Now, what you also did in 1150, likely, is we can define the zero of the potential energy wherever we want, okay, since it's only changes that matter. So we can call zero Earth's surface, or the ground. In this case, y initial is zero, and then at any gravitational potential energy at a height y is just mg y. So there's nothing sacred about making the ground zero, but it's often done in problems because we can arbitrarily set the 0 point wherever we want. Okay, now let's do the same thing with the electrical potential energy. So the work done by the electrical force, the Coulomb force, is equal to the negative change in the electrical potential energy, and this should be equals U and R initial minus R final, since it's the negative. So I'll change that. And let's consider a charge in a uniform electric field. Okay, so uniform electric field, if you recall from the last chapter, exists between the plates of a parallel plate capacitor. Okay, and since this uniform electric field is analogous to a uniform gravitational field near the surface of the Earth, so that's why we're starting here with a uniform field, just to draw the analogy here. Now, since the electric field doesn't have to, unlike gravity, right? Gravity always points down, and so near the surface of the Earth, the direction is always the negative y direction. The electric field can be along any direction, right? We can orient these plates however we want. And so in the spirit of the author's notation, we're going to call this direction S, where S could be the y direction, the x direction, the z. It can be any direction, okay? So we'll call the S direction the distance between the plates, okay? And the work done by the electric field then, if the electric field is along the S direction, some arbitrary direction, is equal to the force, which is Q times E, dotted with delta R, And remember, that's just equal to the magnitude of Q, the magnitude of E, times delta S cosine of theta. Okay, and that's equal to QE. Delta S is the magnitude of S final minus S initial. Okay, and that work done by the electrical force, by the field, is the negative of the change in the electrical potential energy. And so here we get that the equation for that the electric change in electrical potential energy is just QE times the displacement delta S, remember the magnitude, times the cosine of theta. Okay, and let's just, to get our signs right, the signs are the hardest part of this, is just keeping track of your signs. So let's do an example here. Let's suppose that you have the electric field here pointing to the left, and you have a proton, or we'll do a numerical example here in a minute. The proton is going left to right. So in other words, the proton is moving from the positive plate to the negative plate. Okay. Now, we know in this case that the proton is going to be attracted to the charges on the negative plate. So we know it's going to accelerate, right? We know it's going to gain kinetic energy. And we also know that it's going to lose potential energy as it goes near the plate, right? It's going downhill, so it's losing potential energy. So let's look at our signs here. So the work done by the electric field in this case, Q is positive, so this is positive. E, delta S, these are all positives, these are magnitudes. Now let's look at the cosine of theta. Okay, cosine of theta is 0 because the electric field, and hence the electric force, because it's a positive charge, is in the same direction as the motion. So theta is 0, so this is 1. And so in this case, positive work is done by the field. Okay? Since the change in the electrical potential energy is the negative of the work done by the electrical force, then delta U electrical must be negative, which means that the charge must be losing potential energy. And in fact, it is. It's losing potential energy, and it's gaining kinetic energy as it gets accelerated from the positive plate toward the negative plate. Okay, now you could flip this around. You could have the positive charge moving from the negative plate toward the positive plate. Okay, now if we stop and think here, before we get into the signs, it's going uphill, right? Positive charge is going toward the positive plates. These guys are going to repel it. So it's going against the grain here. It's going uphill. And so you might guess that the potential energy should increase and that it's going to slow down, right? Because all these charges are going to repel it. And so the kinetic energy will decrease. Okay, well, let's check our signs out here. The work done by the electric field is Q, and it's a positive charge. E, positive. Delta S, it's a magnitude, positive. But here, theta is 180 degrees because the motion V, or dr, in other case, the displacement, is anti-parallel to the field. And so theta is 180 degrees. Cosine of theta is -1. And so negative work is done by the electric field in moving the positive charge toward the positive plate. And if the work done by the electric field is negative, that means the potential energy will increase. And in fact, it does. So the potential energy increases and the kinetic decreases. And you can do the same thing for negative charges here. It's just everything is flipped. So negative charges going from positive to negative, that's where they don't want to go, right? They're going to be repelled. And so you might guess that the potential energy will increase and the kinetic will decrease, and opposite. So the hardest thing about all of this is just keeping track of your signs. So I like to keep it in terms of this, in terms of deltas, instead of S final minus S initial, because sometimes it can be confusing. if S final is less than S initial, there's a temptation to make delta S negative, when in fact this is always a magnitude. So the sine of Q and the angle theta will guide you to the right sign of W electric, and then the change in electric potential is the negative. So that's the way I like to do it, but some people are different. So similar to the gravitational potential, we can set S, the location S, where the electric potential equals zero, wherever is most convenient, right? Just like gravitational potential, it only changes matter. And so we can call wherever we want zero. And in fact, with electric circuits, for example, a battery, we will often call the negative terminal of the battery, or what is called circuit common or ground, we will often call that point the 0 point of the gravitational potential energy. So we can set the zero wherever we want. That's not a big deal yet at this point, but when we start getting into circuits, it'll become more important in chapter 27 or whatever it is. So the other thing is that we found that the electric field does positive work. It does positive work on a positive charge moving along the field direction, okay? So in other words, when charges move downhill, okay, for example, a plus charge going from positive to negative, right? That's where they want to end up. They're going downhill. The electric field does positive work, right? Because the displacement and E are in the same direction, okay? The electric field does negative work on a positive charge or any charge going against the hill, going uphill. So positive charge is going from negative to positive plate, charge is going uphill, the gravitational field will do negative work. And it's the same with negative charges, it's just all your signs are flipped here. So we're not going to derive this, but if you recall from Physics 1150, that if you don't have any dissipative forces, like friction, and we define our system carefully, that the energy of the system is conserved, mechanical energy, and so the change in kinetic plus the change in potential is zero. Or in other words, the sum of this total energy, initial kinetic plus initial potential, is the same as the sum of the final energy. So in other words, energy is conserved, or mechanical energy is conserved, when there's no dissipative forces, right? Where K, recall, is the total kinetic energy of the system, the sum of all the kinetic energies of the objects in the system, and U is the potential energy due to interactions. Okay, in 1150, this U was almost always the gravitational potential energy. Now we're going to include other types of potential energy, which it could involve as well as electrical potential. So if you just have a charge moving in an electric field, a charged particle, remember the gravitational force on gravity is so much weaker than the electrical force for these light particles, electrons, protons, ions, molecules, so that the electric field dominates and that virtually all of the potential energy is electric, okay? So in this case, we can write conservation of energy for charged particles, where as the change in kinetic plus the change in the electrical potential is zero. And so we can write conservation of energy in this form. So there still is gravitational potential energy between the molecule, or between the charges, because they have mass, but it's just so much less than the electrical force and the electrical potential that for all practical purposes, we can ignore gravity in relation to the electrical force. That's going to dominate the motion. So let's do an example here. So suppose you have a parallel plate capacitor, and we're going to start an electron at the negative plate with zero speed. Okay, so in other words, it's just sitting there at the negative plate. Okay, and you've got an electric field of 20,000 newtons per coulomb, constant field between the plates. And suppose the plates are separated by a millimeter, and we release the electron from rest. So the question is, what's the electron's speed when it reaches the positive plate? Okay, so we know the electron is going to get accelerated, right? We know it's going to, because it's going to want to go toward the positive plate. So it's going to end up with a high speed when it gets here. So let's use conservation of energy, right? That's a lot easier for these types of problems than it is to deal with the electrical forces. Okay, so that's the whole reason why we're doing energy here. So we can invoke conservation of energy. So we can always start by writing delta K, which is 1/2 mv final square minus 1/2 mv initial square, plus delta U is 0. Okay. So then the second step is we write down, okay, what is delta U electric in this case? Well, it's the negative work done by the electric field, which means the negative of Q E delta S cosine of theta, right? Because work done by the electric field, if you go back, is Q E delta S cosine of theta. So the change is negative. And again here, I always like to keep these as delta U's because then it's easier for me than getting messed up with the positions, whether one's a more positive position along the x-axis. It's just easier for me to keep these in terms of delta U's. So what we need to do is we plug in the charge, right? And the charge of the electron is negative E is equal to negative 1.602. What happened to my 10 to the negative 19 coulombs? It should be times 10 to the negative 19 coulombs. I got it right down here. So the charge is negative E. Field strength is E. Spacing is D. And the angle here between the electric field and the displacement is 180 degrees, right? The displacement is to the right. Or to the left, the electric field is to the right. The angle between them is 180. Cosine of 180 is negative 1. So here again, the sign of the charge and the angle will guide you to the right sign. Okay, so that's why I keep everything in terms of deltas. So here I've got a negative, and then negative E is the charge. So those two are going to cancel. And then ED, ed. Cosine of 180, well, that's negative 1. And so the change in the potential energy is negative E, charge of the electron, times the field strength, times D. And then to double check our signs, okay, we're going to get a negative number, right? We're going to get a decrease in potential energy. Let's look here. Well, if you've got an electron, it's going against it's going downhill, right? It's going where it wants to go. It's going from negative, where the other electrons are repelling it, to positive. So it's being attracted here. So the potential energy should decrease, and the kinetic will increase. So our sign is right. Okay, so now I'm going to plug that in for delta U. Okay, and we do that right here. Negative little e times E, electric field times D is 0. Okay. And then we're going to solve this equation for the final speed of the electron. Okay, so we can write 1/2 mv final squared is the initial kinetic energy plus the potential energy, the change. Okay, and the initial speed is 0. So 1/2 m times 0 squared is 0, plus this change in electrical potential energy. And now we solve this for V final, plug in numbers, and you get that the final speed is 2.7 times 10 to the 6th meters per second. So the electron gains potential energy at the expense of a loss in, it gains kinetic energy at the loss of potential. Okay, so the easiest way for me to remember, just looking at the picture, is that if a charge is moving in the direction that it wants to go, in other words, negative charge wants to go to the positive plate, it's going to lose potential energy and it's going to gain kinetic energy. If it's going in the direction that it doesn't want to go, so for example, back here, where is it? We don't have any example. Here's an example. An electron going from the positive plate to the negative plate. Well, it's going to be repelled here, right? It's going uphill. So its kinetic energy is going to decrease and its potential energy is going to increase. So potential energy always increases when a charge is moving in the direction that it doesn't want to go in. It's going to gain potential, lose kinetic. So I think that that's enough for today. We're going to be doing, we're going to continue this for about the first 3 days of next week. We will finish up on chapter 25. Then we get on to a related chapter, which is chapter 26 on the electric potential. And then after that, we're going to have our second unit exam, which will be chapters 22, 23, 25, and 26. So we're talking a couple of weeks, 2 to 3 weeks before your next exam. So that's enough for today. Have a good weekend, and we will see you on Monday.